Imagine predicting rain with pinpoint accuracy 30 minutes before it happens. Think about how much our lives could change if we could truly trust these predictions. Welcome to our research project on precipitation nowcasting with explainable artificial intelligence. We'll take you on a journey through our story, exploring our research and its impactful contributions. First, what is precipitation nowcasting? It's not your average weather forecast that vaguely tells you what might happen tomorrow. Precipitation nowcasting predicts the intensity of rainfall in a specific area for the next few hours with laser-like precision. Imagine knowing that exactly 5 millimeters of rain will fall in a specific square kilometer at 2 p.m. That's the unmatched power of nowcasting. So, why do we need precipitation nowcasting? It plays a crucial role in responding to natural hazards like flooding and landslides. A 30-minute early warning can save countless lives. The aviation and maritime industries already rely on it, and it's invaluable in sectors like construction for daily planning. Even in our everyday lives, a timely notification about impending rain can help us in many ways, at least to take our clothes in on time. Precipitation nowcasting relies on diverse data sources. Rainfall, satellite imagery, wind patterns, temperature, humidity, and topography are just a few. This data is fed into a machine learning model, a kind of black box, that predicts precipitation patterns for the coming hours. This is the essence of precipitation nowcasting with machine learning, a well-established and rapidly evolving field. Now let's talk about the next part of our title, Explainable Artificial Intelligence, XAI. Why do we need XAI? Machine learning models that integrate multiple data sources have dramatically improved prediction performance. But how do we build trust in these advanced AI models, especially among researchers who have spent their careers relying on traditional methods? We need to show them that the model's predictions are based on understandable, logical reasons. That's where XAI comes in. Looking into our previous diagram, we can use explainable AI to see what is happening inside this black box. The novelty of our project lies in developing a methodology to demystify these AI black boxes. So how are we doing this? First, we prepare the data. We use a public dataset named MeteoNet, which combines rain radar, wind speed, and satellite data over 3 years. We process this dataset to create multiple 1-hour-long input sequences by stacking all the images from that hour together. Our goal is to predict rain 30 minutes ahead of these input sequences. Hence, we use a binarized rain radar image 30 minutes ahead as the target. Then, these sequences, along with their targets, are fed into a machine learning model for training. We use the UNet architecture for this task. After training, we evaluate several samples from our test dataset. We input the sequence, and the model outputs the precipitation map 30 minutes ahead. Here's an example. You can see the input sequence, which includes 5 rain radar images taken 15 minutes apart, 2 wind speed images in the U direction, 2 in the V direction, and 2 satellite images, each 1 hour apart. At t equals 90 minutes or 30 minutes after the sequence, this is the actual observed precipitation. The model's prediction closely matches this observation. After testing 916 samples, we achieved an average F1 score of 0.76, which tallies with the existing research. Once the model prediction is complete, we move to the core of our research, explainable AI. We use a modified version of integrated gradients to determine which areas in each input image the model focused on. Integrated gradients track how gradients change from input to prediction within the neural network, creating a map that highlights the most influential areas in the input. With this, we can isolate each image in the input and see how influential they are. We then calculate the sum of integrated gradient values on a log scale for each image and plot it. This gives us the relative contribution from each image in the input sequence. As you can see, the rain radar image at t equals 60 minutes and at t equals 45 minutes, followed by the satellite image at t equals 60 minutes, contribute the most. We were able to confirm that the observed pattern is correct by building multiple models isolating different data combinations. Also, it makes sense that rain radar images are top contributors since they directly measure rainfall. The image closest to the target at t equals 60 minutes, being the most influential, also aligns with expectations. These factors confirmed that the observed results from integrated gradients are acceptable and correct. Identifying these top contributing images led us to a significant insight. By selecting only the top 3 contributing images, we reduced our input sequence from 11 images to 3, cutting the size by more than 2/3. We retrained the model with this reduced input and tested it. Remarkably, there was no noticeable decline in performance. This proves we can use this method as a dimensionality reduction approach for these datasets, simplifying models for future researchers and aiding in miniaturizing models for production systems. In conclusion, our research makes several contributions. 1. A machine learning model for predicting precipitation 30 minutes ahead. 2. An explainable AI method that identifies which regions in each input image the model focuses on. 3. An assessment of how much each image in the input sequence contributes to the final prediction. 4. An evaluation of how much each data source contributes to the final prediction. 5. A successful dimensionality reduction technique for precipitation nowcasting datasets. We also developed and deployed a tool to demonstrate our findings. Let's conclude with a demo video showcasing this tool. The application is deployed on Hugging Face under the displayed URL. The first tab summarizes the research methodology we used here. The second tab outlines the resources used. The final and most important tab, XAI, will allow for a hands-on demo. You can download an input sample sequence directly from the application. Here, I've opened the downloaded folder. You can see in the shown folder, there are 11 images and the target image. These images form the sequence. You have 2 upload options. You can either rename the images to the expected format and use the first upload option to drag all the images at once, or you can select the second option and upload images one by one into their respective slots. Let's use the first option here. Once done, you'll see the processed sequence and then the prediction. If you include the target image in the input, performance scores will also be calculated. After predictions, you'll be able to see the explainable AI results from the application's output. This concludes our presentation on the research project. Thank you very much.